Hello everybody, this is Professor Sadigin from Indiana University East, and we are gonna actually start the portion of the course which is addressed to students of M511. Specifically, we are gonna speak of measure theory. There are different types of measure theory in mathematics. We are, in fact, concerned with Lebesgue measure, which is on the subsets of real numbers. In other words, this is really related to real variables and real analysis. For example, probability is itself a measure, but it's not on the subset of the real line. There are similarities, but in this course, we are actually concerned with Lebesgue measure, as I mentioned. We assume students are familiar with subsets of the real line, different types of subsets. These are steps that some of you might have even seen in calculus, definitely in real analysis part 1. You should have seen it. What is an open set? What is a closed set? What's a compact set? Of course, there are definitions for each. There are definitions which are equivalent for each. For instance, you can define a closed set to be the complement of an open set, or you can say, well, a closed set is a set which contains all of its accumulation points. You have seen those in early courses. In other words, specifically, I'm talking about real analysis 1, which is really a prerequisite for this course. Sometimes I review some of those because I assume some of you could have forgotten, but in general, you should know what is, for instance, a compact set. Also, I ran this part of the course as a graduate course. By that, I mean, even in my lectures, I ask questions, some of the properties, or for instance, a fact that is stated in a theorem is not proved. In fact, I put it as a problem. I'm gonna write set up problems for each lecture or each section we cover. So but they sometimes come from the lecture, and you see, I mean, there are locations in the lecture that I write in parentheses why. That's actually your duty to investigate and see why. In other words, that's a problem. Now, the Lebesgue measure is a very, very interesting topic. Lebesgue, of course, is a famous mathematician, and this branch of mathematics is named in his honor because he's the mathematician mostly worked in this area. Now, in here today, we are going to talk about measure of open sets and compact sets. In fact, probably I don't want to make these lectures very long, because it can be tiresome for some of you. So I might divide it into two. We may not get to the measure of compact sets or even finish open sets completely today, but we are going to prove some results, make some definitions, and so on. Now, the idea of measure starts with a very simple concept. The length of a finite interval is its measure. If J is an interval, we define the measure of J, which we denoted by M of J, to be the length of J. So if you have the open interval from A to B, or if the left point is not included, A to B, and the right point is included in the interval, or bracket A, comma, parentheses B, you know all of the definitions here, and you see the, I hope at this point in this course, the difference says, and the closed interval A, B, all of them, their measure is the difference between B and A, B minus A. Very natural, very commonplace. The length of an interval is its measure. Now, intervals, of course, can be unbounded. You see, A to infinity, infinity to minus infinity to B, open, closed, anyway. At B, it can be parentheses or bracket. All of these are infinite intervals. And for these, obviously, you intuitively know the length is infinity. And that's what we do. We define the length for these intervals to be infinity. So we are going to deal naturally with the symbols infinity and minus infinity, and we have to see how to deal with them specifically in this course. So we are going to follow some rules, very simple rules, which I have put here. If you add any number x to infinity, the result is infinity. If you subtract infinity from x, the result is minus infinity. If x is positive, and then you multiply it by infinity, intuitively, you know that you should get infinity. That's what your common sense tells you. And if you multiply x by minus infinity, assuming x is positive, you get minus infinity. Now, if x is negative, the rule will be changed. X times infinity is minus infinity, and x times minus infinity is infinity. We take infinity minus infinity to be infinity minus infinity minus infinity to be minus infinity. Infinity times plus and minus infinity is plus and minus infinity. Those rules which are actually defined intuitively. Those concepts that you should just know intuitively. Now, the only time that we have difficulties minus infinity plus infinity, which we take it to be undefined. However, we define 0 times infinity to be 0. So these are some conventions. Now, you know what an open set is, but in case someone has forgotten it, I may write the definition here, the very basic definition for an open set. A subset E of real numbers that are with I in front of it, just a notation, that means the real number. That's a kind of R. But in my typing, it's a little hard to write it, but that's what R is, basically, a script R. Subset E of R is open if for every X in the set E, there is an open interval A to B, so that the entire open interval is a subset of E. Definition of an open set. Closed sets are defined differently, but they are all equivalent. A subset F of real numbers, a set of real numbers, is closed if and only if its complement is open. FC means complement of F. What's the complement of F? Means every real number which is not in F. Review your set theory or foundation of math or whatever you call it. So complement of F means all elements of the real line which are not in F. Okay, here just have a little practice. Which of the following sets is open? -2 to 5, parentheses at both sides. Obviously, that's open. In fact, it's an open interval. You know, -2 to 5, but at 5 we put a bracket. That's not open because around 5 you cannot have any little interval which is completely in this set, right? C is open, right? In fact, the union of two open sets is an open set. Again, going back to early facts about sets of real numbers. A countable union of open sets is an open set. That again is a fact about open sets that you should know. A subset C of real numbers is compact if and only if it's closed and bounded. Well, closed, we mentioned what it means to say this set is closed. Bounded means you can assume your set C, for instance, in here, is a subset of an open interval from A to B. Bounded means it does not extend to infinity from either side. Theorem. This is actually a key theorem in measure theory. We use this theorem to define the measure of an open set. See what it says. If U is an open subset of R, then there exists a finite or countable collection In of pairwise disjoint open intervals. Pay attention to pairwise disjoint. They are disjoint from each other. Open intervals so that U is union of these open intervals. The collection In can be a finite or a countable collection. Now here is a proof. And the proof, really, when you look at it, is straightforward, but there are very delicate points in it that you have to watch, and little things that you have to explain to yourself. Okay, so U is open. Take an X in U. Since U is open, there exists an epsilon such that X minus epsilon to X plus epsilon, that interval is a subset of C by properties of open sets. In particular, S to X and X to T are subsets of E for some S smaller than X and some T greater than X. You see, first, the center we assumed is X, and it goes epsilon to the right, epsilon to the left, but we don't know that's the largest one, so we want to find the largest one. So we assume that on the left of X, it starts from S, and to the right of X, it ends at T, that interval, and it's not a symmetric interval. In other words, X is not in the middle. We don't know. We just say it's an interval. Okay? Now, and it may not be unique. You might have a bunch of them, but here is what we do. We take the largest one from right and the smallest one from the left. Suppose R of X is equal to supremum of T on the right side we are now looking at, T, so that X T is a subset of U, and left of X is similarly the infimum of Sx, so that the set S from to X, the set interval from S to X, X included, is a subset of U. Now, obviously, X is less than R of X. X is greater than T of X for any X that you have on the interval U. Now, let I of X be the interval whose left side is L of X and whose right side is R of X. Now we assume, we don't assume, by the construction we had, this interval is the largest interval, right, that you can imagine, which is containing X and itself is inside U. Well, first of all, it's inside U, this interval. I put a Y here so that you really make sure that this interval which we constructed this way around X is in U. The proof is not hard. Actually, I'm going to put a set of very simple problems. One of them is this, that, and I just refer in the problem, this is the Y, the first Y in the theorem we had, instead of probably stating the whole theorem again and ask you to prove as a problem. So definitely the interval we construct this way around X, L of X, L sub X to R sub X is inside U. Furthermore, and that's also something you can think about it and prove it. If X and Y are two different points in U, then the interval associated with X is equal to integral associated with Y, or else they are disjoint. So either they're equal completely or they're completely disjoint. Those of you who had set theory, you know what this kind of property is. Equivalence classes. In fact, these intervals form an equivalence class. For X and Y, two different points, either the interval associated to X and Y, I of X is equal to I of Y, or else they're completely disjoint. Their intersection is empty. That needs a little thinking. That's why I put Y, but it's easy to prove. I put it as an exercise for you. Okay, now we continue the proof. So those two properties are there. I of X is subset of U for every X, and if you have two numbers X and Y in U, two elements of U, then either the associated intervals I of X and I of Y are equal or completely disjoint. Now we continue the proof. To complete the proof, let W be the set of all of these intervals which we constructed. And Q, as always, represents the set of rational numbers. For each interval I in W, actually, we omitted X as a subscript here because now we can just be relaxed and call one element of W just I. Choose a rational number that you call it R of X, such that R of X being that interval. That's possible because, you know, rational numbers are dense. That means every interval has a rational number, so they're rife in that interval, but choose one of them. Choose one of them and call it R of X. Now, if you have two of those intervals that we just constructed, two of them, one of them I, one of them J, which belong to this set W, and they are different, then the rational number you choose in I is different than the rational number you choose in J. Obviously, because I and J are disjoint. Why they are disjoint? Because we say distinct. They are two distinct. Each of them has a rational number in it, and their rational numbers are different. Therefore, the mapping that takes an interval I to its rational number is a one-to-one mapping from W to Q. And therefore, the collection W is at most countable. When you say at most countable, means it's either finite or countable. These are actually concepts in set theory, right? Anything that you can number it 1, 2, 3, 4, it's countable, and so on. And finite is obviously when you have a limited number of them, it ends. So that is countable. And if it's countable, then as I just said, you can numerate it. You can write I1, I2, I3, I4, and I infinity, right? And obviously U is equal to this union. Each of them is in U, obviously. So the union is in U. And U is in the union because when you pick an element of U is in one of those I's. The way we constructed it. This is actually a very important theorem for us because it allows us to now extend definition of measure to open sets. How? This is the definition here. If U is an open subset of R with U equal to union IN and equal to, well, if it's countable and is from 1 to infinity, if it's finite, it's just finite. So to make sure that we cover both, we don't put anything here. We write union IN, where the collection IN is the final or countable collection of pairwise disjoint open intervals. We simply define mu m of U, measure of U, to be the summation of the measure of IN. Very simple. Now, I have a few remarks here to make. For the empty set, we always say its measure is 0. So the measure of empty set is 0. That's one point you have to remember. Now, the sum which defines the measure, this summation here, might be infinite. Or it can be finite. For instance, if any of the intervals you take has infinite length, then obviously m of u is infinity. You see, if one of those I sub n's is an infinite interval, the measure of u is infinity. Also keep in mind, on the other hand, if the INs are pairwise disjoint, we still might have the measure, which is really a series summation n from 1 to infinity of measure of in be infinity, right? That's a series. It's not a regular sum in the case that in is countable. And a series can be divergent, or it diverges, or it can diverge to infinity. It's actually a monotonic increasing series whose sum is either a real number or it diverges to infinity. So a measure can be infinity. Let's look at some examples to explain these situations. Here are a few examples. For each n, define in to be the interval from n minus 1 over 2 to the n. I'm sorry, please correct this. There is a typo here. N minus 1 over 2 to the n to n plus 1 over 2 to the n. So the n, the 2 at the exponent is wrong. Put it n, 2 to the n. Then n plus 1 over 2 to the n, again, this should be n, is less than n plus 1 minus 1 over 2 to the n plus 1. And this inequality here really shows that these intervals are disjoint. And if U is the union of these disjoint intervals, by definition, its measure is the summation of the measure of each, and the measure of each would be 2 times 1 over 2 to the n, and when you add all of them, this series converges to 2. So this is a very nice example to show you that a set can be unbounded like this set, but its measure be finite. This is an unbounded set with finite measure. When we say finite measure, means the measure is not infinity, it's just a finite number, a regular number. So this was an unbounded set with finite measure. In fact, the opposite also can happen. You can have a bounded set with infinite measure. That we get to it in a moment. Let's look at another example. Now, look at this collection of open intervals, in, where the end point is n and the right one is n plus 1 over n. And take V to be the union of these open intervals. Again, measure of V by definition is summation of measure of each j n. And in this case, you are going to have this series summation n from 1 to infinity of 1 over n, and from your calculus, you know that summation n from 1 to infinity of 1 over n is infinity. Now, this is an example of an infinite unbounded set which has also infinite measure. Now, the last one, example C, is interesting, and I'm going to actually give you one problem on contour set. I think I misspelled contour here. If that's the case, I apologize. But I give you a problem on it. Some of you have seen this in real analysis 1, and they use this set. This is one of the nicest sets in mathematics, good for a lot of examples. You look at the interval from 0 to 1, okay? Here is how you construct a contour set. I'm going to write this statement as a problem for those who you forgot. You look at the closed interval 0 to 1. From the closed interval 0 to 1, you take 1/3, which is in the middle, out. Okay, so you go from 1/3 to 2/3 and take the open interval from 1/3 to 2/3 out from this set. Then there are two parts left, to the right and to the left. Then from each of those, you take 1/3 of them, which is open out, and you continue this. What's remained is called the contour set. What you take out, the complement of the contour set in the interval 0 to 1, is just a complement of the contour set. It can be shown that the sum of the length of all of the intervals that you take out is equal to 1. However, that's a bounded set. So you can have a bounded open interval with finite sum. I write a problem. I write this statement on the problem and actually remind everybody of a contour set if you did not have, and you work on it more here. Okay. So U here is the union of the open intervals that have been removed, as I mentioned, by property 4 of the contour set. Measure of U is equal to 1. Actually, contour set. I don't know if I exactly pronounce this name correct. It's contour or contour. This particular interesting set has 7 properties, one of which is that the measure of the parts that you take out together, all of it is 1. In other words, the sum of the lengths of all of the intervals that you take out from the middle is 1. Okay, so in fact, this is property number 4. It has, as I mentioned, 7 important, nice properties in mathematics. Okay, we talk about this problem more, this counter set more in a exercise or problem which I put for you. A very innocent, simple looking theorem that you might say, oh, it's a piece of cake. But it's not that piece of cake in measure theory. Remember, in measure theory, you are dealing with series, the way measure is defined. So don't take anything just simple because it looks simple, because you think, yeah, that makes sense. If U and V are open subsets of R and U is a subset of V, then what do you expect? Measure of U is less than or measure equal to measure of V. Now this is really misleading. I mean, because you think, well, it's easy. Why? Because you are looking at, for instance, sets, right? I mean, if set A is a subset of set B, I mean, you have a set of pencils, and if you take a subset of it, you know, the subset has a smaller number. In fact, number is a measure, but not Lebesgue measure, though. We are talking about Lebesgue measure here on intervals. Now, this, with that concepts that you have in mind, you might think this is simple, but it's not. Okay, so the statement of the theorem appears to be obvious, and you might tell yourself there is no proof required here. However, it is important to know that how we define measure. A measure was defined as the sum of a series. Okay, so here is what we do. We go back to the definition of measure. Suppose U is union of n INs. It can be finite or infinite union. And V be union of GMs. We are using N and M because we don't know if their number is the same for U and V. The number of intervals which compose U might be, the number of them might be different than the number of intervals that compose V. Where IN and JM are finite or countable collections of pairwise disjoint open intervals. Now, since U is a subset of V, for each interval IN, you have it in some GM because U is a subset of V. At least when you look at each of its interval, it should be in an interval of the bigger set. Think about it. Now, of course, one interval of the larger set V can contain more than one IN. define n sub m to be all integers n so that I sub n is a subset of G sub m. You see, because set V is bigger, one of its intervals, Gm, can contain a bunch of the intervals of the smaller set, U. And that's what we are saying here. We define n sub m to be all integers n so that I sub n is less than G sub m. Since the collection Gm is pairwise disjoint, so is the collection Nm. Does it make sense? Because if you take M1 and M2, for instance, GM1 and GM2, NM1 is different than NM2 because these two intervals are disjoint themselves. So then all of the GINs that GM1 has are different than the ones that JM2 has. You have to think about these very carefully. So the collection NM is also disjoint, and you can write mu m of u, measure of u is equal to, first of all, you can write measure of u is equal to, here you don't need measure at the beginning because just it's the set u. You can write u, so cross out that measure. You can write u is equal to union of INs, obviously, which now you can write it is union of M, then union of N belongs to capital N sub M of IN. So you put them in groups, in other words. See, you put your INs in groups. Each group belongs to, each group, each element, each member of each group is subset of a GN. So you can write U is equal to union M. Again, union of N belongs to N, capital N sub M of I N. And therefore now we bring the measure. Measure of U is equal to summation of measures of IN. The measure is missing here and is equal to summation on M, summation of N belongs to N sub M of measure of IN. However, measure of IN is smaller than or equal to measure of GM. Why? Because IN is a subset of GM for every okay, this is actually more than one of them. This is the sum of them. However, summation of measure of INs, which are in GM, which are subsets of GM. So to see the sum of the measures of those INs that each of them is a subset of GM, when you add them up, is less than measure of GM. because they're disjoint and they're all of them in GM. So when you add them up, all those measures is smaller than or equal to GM. And from there, the result follows. So the proof of this simple fact theorem, if you really want to go back to the definition of measure, is not that trivial. I mean, you have to keep that in mind when you are dealing with measure theory. Some of the theorems and results look simple, however, their proof is not that simple. As a result, we can say that if U is an open subset of open interval A to B, then obviously measure of U is less than B minus A by what we proved, because of the fact that measure of A to B is B minus A and measure of U is less than B minus A. And we can put this in another statement. You can say, thus, every bounded open set has finite measure because its measure is less than B minus A. If it's bounded, it's in by definition of bounded, a bounded set is a set that is subset of an interval B to A. So if it's a subset of an interval B to A, then you can say its measure is less than B minus A, and therefore the statement here is correct. Every bounded open set has finite measure. Now, we are going to prove some more theorems on measures, but we need to remember some definitions we had in calculus or real analysis 1. Remember the definition of characteristic function. If E is a subset of the real numbers, then the characteristic function is defined by, well, here we show it as x sub E of little x. That big X is just a notation for the characteristic function. But x is a real number, which is in E, or not in E, is a real number. Characteristic function at little x is equal to 1 if and only if x is in E and 0 if it's not. Now, we have a little discussions here which is necessary for theorems that we want to prove later. And we want to, in fact, relate things to Riemann integral. Well, we are going to discuss Lebesgue integral later, but this is your Riemann integral. which you see in 303 M314, but you have seen in calculus. It's not new. Riemann integral. Suppose I is a bounded open interval. Choose A and B such that I be inside the closed interval A to B. Characteristic function of I obviously is continuous on the closed interval A to B, except at two endpoints of I. X of I is integrable on the interval from A to B, and the integral of the characteristic function of A x characteristic function of E. If you look at the characteristic function of E and integrate it from A to B, that's nothing but measure of I. So I is a bounded open set. You put it in a closed interval A to B, and you see on parts of the closed interval A to B, which does not have anything to do with I, in other words, I is a subset of A to B. On those parts, your function is defined to be zero. So when you integrate the characteristic function of I from A to B, you get measure of I. That's something to keep in mind. A very smart way to define measure of a bounded open interval. Be careful. Not bounded open set. You're talking about bounded open interval. Can be expressed as the Riemann integral. Measure of I is equal to integral from A to B of characteristic function of E and of course this definition is unique. In other words, if you choose another closed interval that contains the open interval I, bounded open interval I, well, because you define outside of the I to be zero, so it doesn't matter what's the length of, the interval which contains it. I mean, take CD, but CD be larger. Well, I mean, no matter how the length, how much the length or the size of the closed interval is, characteristic function is zero outside of I, and it doesn't affect really the integral. So that's actually the comment here I make. It should be clear that this is independent of the interval A to B containing I. Now, we focus on open subsets. If U is an open subset now of AB, with U be equal to a finite union K from 1 to M of JK of open intervals, which are pairwise disjoint. So J subcase are pairwise disjoint. U is an open subset of closed interval A to B with U be union of J sub K. Each of these J sub K's is an open interval and they are pairwise disjoint. If that happens, the characteristic function of U is the sum of the characteristic function of these J sub K's. That makes sense. Think about it because they are disjoint and the characteristic function is either 1 or 0. And if you take that union and you take an arbitrary x, it belongs to one of those J sub K's only. And on that J sub K, its characteristic function of J sub K is 1 and otherwise 0. So this makes sense. You can say characteristic function of U is equal to the sum of the characteristic functions of Jk. Now you integrate. If you integrate this, then you have measure of U is equal to summation k from 1 to m of measure of J sub K and change it to integral is equal to summation of k from 1 to m of Riemann integral of characteristic function of J sub K dx, which is equal to integral from A to B of characteristic function of U. So we extended the definition of measure to be a characteristic function integration now to an open set mu. An open subset which is a finite union of J sub K. In fact, we won't go to infinite union, but we are a little shy. Now we work with finite, we have more theorems here to prove interesting theorems, but this is for finite. If U is an open set, which is the union of finite collection of disjoint intervals, open intervals Jk, then you can see that mu of U is also equal to integral from A to B of characteristic function of U dx. Okay, we had all of these discussions which I made here, looking at measure of certain open sets as Riemann integral to be able to prove the lemma we have in here. And this is the last item in this lecture. To not make it too long, I'm gonna actually give another lecture which is continuation of this, and it will use this lemma. Here is the lemma. If the collection IN is a finite collection of bounded open intervals, then measure of union of these INs is less than or equal to summation k from 1 to n of measure of each of them. Measure of union is less than or equal to summation of measures. Now be careful here, we do not assume these intervals are disjoint. If they are disjoint, we have equality, obviously, right? By definition. But if they're not disjoint, what happens? That's what happens. The measure of the union is less than or equal to summation of the measures. Again, you might think this is an easy thing to prove. Not so fast. What you really have in mind is other measures that you have seen in your life. For instance, probability, right? Everybody knows probability of A union B is less than probability of A plus probability of B. That's actually a different kind of measure, but here we are dealing with Lebesgue measure, hard stuff on the real line, which are defined by summations, which are actually really series in a way if you have countably many. But of course here we have a finite number, but still it's hard because still it's a summation. So going back, looking at the statement of the lemma, see what we have here. If IN is a finite collection of bounded open intervals, not necessarily disjoint, then measure of their union is less than or equal to summation of their measures, in other words. And here is an interesting proof based on the discussions we had and changing things to Flamin integral for certain sets, measures to Riemann integral. Okay, let's look at the proof. Let the collection be a finite or infinite collection of bounded intervals, and let U be the union of them. Choose A and B in real set of real numbers so that U be a subset of AB. Why? Because we say it's bounded. Then characteristic function of U is continuous except at a finite number of points. What are those finite number of points? Possible finite number of points? Those are the endpoints of those intervals, I sub n. Okay. And in real analysis, one should have seen this, that if a function is not continuous at a finite number of points, still it's integrable on an interval. You see, if it's not continuous at finite number of points, you just add the integrals I mean, if it's not, for instance, continuous at a point C, you write integral, you exclude point C and there are a number of intervals, and still you can say it's integral. So the characteristic function of U is continuous except on a finite number of points, and since it's continuous on a finite number of points, you can have its characteristic function less than or equal to summation n k n from 1 to capital N of x of Inx. In other words, its characteristic function is less than or equal to the summation of the characteristic functions of those sets which make it up. Actually, then by the last identity we had before the discussions we had above in here, by this identity we are talking about, that for intervals, measure of the interval is integral of the characteristic function. You can replace measures with integration. So you can write integral from A to B of characteristic function of U, which is m of U, is equal to summation k from 1 to m of each jk. Oh, actually, let me go back. That we proved for the. I came back. Sorry. There is the lemma. I again went back to the. Where did the lemma start? Okay, lemma. I was confused with the previous discussions we had before the lemma. If In is a finite collection of bounded open intervals, then measure of the union is less than summation of the measure of each interval. It should be mentioned here that we are not assuming they are disjoint. Now, I'm repeating the proof. Let In be a finite collection of bounded open intervals, and let U be their union. Choose A and B such that U is inside AB. Then characteristic function of U is continuous continuous on AB except a finite number of points, and explained what those points are. Those points are possibly the ends of those intervals In, and therefore we can write characteristic function is less than or characteristic function of x is less than or equal to summation k from 1 to n of characteristic functions of each interval. Why less than instead of equal? Because two of those i's can overlap. You see? And if they overlap, the value of the part that they contribute to this summation would be 1 plus 1 makes 2, right? While characteristic function of x can be maximum 1. So that's why it's less than or equal. And therefore, we can write measure of u is equal to integral from a to b of characteristic function dx is less than or equal to summation from a to b n from 1 to n of characteristic function of the integral of those characteristic functions. In other words, put integral sign on everything here. That's what we get. And finally, that becomes summation n from 1 to capital N of m of I sub n. So measure of u is less than or equal to summation n from 1 to capital N of m of I sub n. The tricks that we played here are actually unique to replace measures with integrations of characteristic functions. Regardless, the proof is complete here. Measure of union of a bunch of open intervals. Union of a bunch of open intervals. Sometimes notations make it really harder to see what we are talking about, but if in simple language, you can say measure of union of a finite number of open intervals is less than or equal to summation of measure of those open intervals. And we are not assuming they are disjoint. If they are disjoint, is equal by very definition of measure. Okay, I stop here. Next time, we are gonna actually use this lemma to prove more theorems. And I'm gonna actually write a few problems for you to do.